Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresh University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science, and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Okay, so good morning, everyone in Thailand, but it's a little bit late in, I guess, in Mexico, right? Okay.
Yes.
And welcome everyone to IF Colloquium number 32. Sorry, there is a typo in the poster, but actually it's number 32. And today we have a very, very special guest, Professor Hernando. Cubillos. Sorry if I pronounce your name is not quite good. So he's a professor at and researcher at Department of Gravitation and Field Theory, Institute of Nuclear Science, National Autonomous University of Mexico. And today he's going to talk about Geometrothermodynamics cosmology, which is actually a very interesting topic. And so, if you're ready, Professor,
Yes,
you can.
yes, I'm ready.
Yeah.
Okay. First of all, thank you very much for this kind invitation to give me the possibility to present you some of the subjects I've been working for the last years. So, I am going to talk about cosmology, which I suppose you all know what's the idea of cosmology, but from a different point of view. So the point of view is from the point of view of thermodynamics and from the point of view of a recent formulation of thermodynamics in terms of differential geometry, which we call GTD, Geometrothermodynamic. Okay, this is the idea. So the point is that we have found in the last 7-8 years that it is possible to apply these formalism, the formalism of geometrothermodynamics in cosmology. And this combination of these two theories, this is what we call geometrothermodynamic cosmology, GTD cosmology. So let me start with the outlook of my talk. First, I'm going to recall you about the idea of the standard cosmological model, which is what we call lambda CDM, which is a part of the standard cosmological model. And then I am going to talk a little bit about inflation, about the most popular model we use today in order to understand our universe. So then I'm going to point out that there are some problems in these standard cosmological models, and this is the way why this is the reason why there are so many alternative formulations of cosmology. And I'm going to present one additional formulation, which is what we call GTD cosmology. For this, we need to explain what is GTD, and then after some brief explanation, I will try to put together these two formalism, GTD and cosmology, and to formulate a geometrothermodynamic model for the universe. And in doing that, I'm going to present you what we call the fundamental equation of the universe. Then I will present the exact, some of the parts of the model, the exact parts of the models. Then, starting from GTD, I will show that it is possible to talk about an inflation without an inflaton, which is one of the problems of the standard cosmological model. Then I will present some ideas about perturbations of this model, and I will finish with some conclusions. So please feel free to stop me at any moment if you want me to explain something in more detail. So then let's start with the standard cosmological model. What's lambda CDM? The first thing we should know is that in order to explain the universe today, we use what we call the cosmological principle, which means that our universe, the universe in which we live, is homogeneous and isotropic at large scales. That means large scale means of the order of magnitude 300 megaparsec, something like that. Okay? Then this is some representation. This picture here, I have some representation of the universe as we see it from a very large scale. So let's take in this representation 2 points, P1 and P2. Okay, these 2 points is any 2 points in our universe. So, and the distance squared between these 2 points is what we call ds squared, the line element of the universe. So, by using now the principle, this cosmological principle, and using some ideas of differential geometry, which means the following. To the point 1, we assign a particular coordinate, which we call t, r, theta, and phi. And to the point P2, we assign a different coordinate, different set of coordinates, which is t plus the t, r plus the r, theta plus the theta, and phi plus the phi. So this is something very well that we know very well in differential geometry. And this is the way how we try to explain cosmology in general relativity. So the first thing is that we have to propose a model for this distance between these 2 points and the universe, and this is what we call the metric of the universe at large scales, which has the names of the researchers who work on this, the physicists who work on this problem. This metric is called the Friedmann-Lemaitre-Robertson-Walker metric. So the form of this metric is based on this idea of having 2 points and the distance squared between these 2 points, which is d squared, the line element. So in this case, one can show that the line element has this particular form in which we have only one function, h, with a with depends on t, which is the scale factor, and then we have r, theta, and phi as the coordinates, and here we have only one term. So there is a question there. Please go ahead. Is there a question there? I saw a hand here, so yes. Saikat,
Yeah.
Chakrabarty, do you have a question? Sorry, I can't hear you.
I think that he just dropped a say hi.
Okay. Okay. Sorry. Hi. Nice to see you, Saikat. Very good. Okay, let me continue. So this is okay. No question. Nice to meet you, Saikat. Okay. So this is the line element, what we call the distance squared between these 2 points, is given in terms of these functions we have here. This is, I suppose you know that quite well. This is the metric of which we use in order to describe our universe. The only two things we have here is this function a, which depends on t, which is called the scale factor, and this constant k, which has to be with the curvature of the universe, the spatial curvature of the universe. So we take this metric and we put this into the Einstein's equations, which is the fundamentals of gravity, of general relativity. These are Einstein's equations, as you know. And then with this metric, with the FLRW metric, we can calculate the left-hand side, which is the Einstein tensor of the Einstein's equations. And for the right-hand side, we suppose that our universe is described from the physical point of view as a perfect fluid. So that means that we have only two parameters, two variables, in order to describe the universe. In this case, is rho, the density, and p, the pressure. So the energy momentum tensor, which is this T mu nu I have here for the universe, in this case is what we call the energy momentum tensor of the universe, the perfect fluid representation of our universe. So then one can put everything into the Einstein's equations, and one can see that the resulting equations, which we call the Friedmann equations, are these ones. We have one first-order differential equation for A. Remember, A depends on t. This dot means the derivative with respect to t. And this is a first-order differential equation. We have a second-order differential equation for A. And so the differential equations are given in terms of rho, as you can see here, rho and p, in terms of density and pressure. So the problem here, which is very well known, is that we have two equations. So from Einstein's equation, we have only two equations, but we have three unknowns here, which are A, the scale factor, rho, and P. And as we know, it is impossible to solve a set of differential equations in which the number of unknowns is larger than the number of equations. So this is why we usually add an equation to this set of equations, an equation which we usually call the equation of state. And this is the way we now solve the differential equations of general relativity in order to understand our universe. So the standard way to do that is that we assume what is called the barotropic equation of state, in which P is related to rho, the density, but means of this constant, which is called the barotropic constant. And so then we can integrate this equation. This is the main point here. Now, and how do we know that we can choose this particular equation of state? We don't know. We just use it, and people decided to do it at the very beginning, probably because this is one of the simplest choices you can use. And so it turns out that this symbol is very simple. This model is very simple, and in fact, it explains the universe the way we see it today. The idea is that there was first an epoch of the evolution of the universe, which we call the radiation-dominated universe, in which this constant, the barotropic constant, is equal to 1/3. Then this was the first epoch of the universe. Then there is a second era, which is with the W equal to 0. This is what we call the matter-dominated universe. And then with W equal to -1 is what we call the vacuum-dominated universe, or the dark energy-dominated universe. So this is how we understand today the standard cosmological model, starting from the radiation. So this is called the lambda CDM model, because lambda represents the vacuum-dominated universe, which is the cosmological constant, and then CDM is the part of the matter-dominated universe, because we now know that cold dark matter is the most important part in the matter-dominated universe. So this is how we understand the universe, and this is a part of the standard cosmological model. So, but we have now We understand the universe, so there is there is something here at the beginning, which from the last formalism I explained to you, from the last model, we don't understand. But this is here the scale factor in terms of time, the cosmic time. And what we know is that all these three epochs I mentioned of the universe, so they're represented here. We have that the scale factor is always an increasing function of t, so that it becomes here what we call the radiation dominated universe. And so it evolves in such a way that today the age of the universe is about 14 billion years, and this is the universe how we see it today, which is dominated by dark energy. Before that, there was an epoch dominated by matter, which is when galaxies were formed, and so on. And before that, we have the radiation-dominated universe. So this is the idea of the universe, of the standard cosmological model. However, we have some problems with this model, and the standard way of presenting this problem is that the first one is the horizon problem, which means that we get light, so to say, from one side of the universe, and we get light from another side of the universe, which is represented here in this way. Today we are here, and we observe light from one direction, we observe light from another direction, and if we go back in the evolution of the universe, we can see that the points A, from which the first light is coming, light rays coming, and points B, they were never connected in any way, so it is impossible that they would have the same temperature, the same, so to say, a characteristic for light coming from these 2 points. This is why I believe we have to change somehow the idea of the universe coming from some special state which were not connected back in time. So this is the reason why we introduce now for these 2 points something different, which is called inflation, in order for these 2 points to be related, to be connected in some way before they started here at this age, which is where we observe this light coming from the past of the universe, which is about 500,000 years. So we have, this is a problem we call the horizon problem. There is no way that light coming from one direction and light coming from another direction, they would have the same characteristics, so to say. We don't know how to do that. Another problem is that according to modern results, it is one of the most interesting results of observational cosmology that K, that constant which is in the Friedman-Lemaitre-Robertson-Walker, is equal to 0. But if we go back in time, that this constant, of course, this is some experimental result. This constant should have this number, which is 10 to the minus 60, which is a very small number. That means that if we have even a very small perturbation of this number back in time, then we would never have the universe we have today. This is called the flatness problem, which means that we have to suppose that there is a fine-tuning process in order to have a value of this constant K, which is so small. This is a problem we don't understand. So another problem is that according to observations, today we don't see practically any magnetic monopoles, and we know that in nature, according to the ideas we know about the standard model of elementary particles, in which the Maxwell theory, the electromagnetism is very important. We know that there were at the beginning magnetic monopoles and electric monopoles. The electric monopoles are the electrons we know today. However, there are no magnetic monopoles. How is that possible? So this is a problem which is related to the origin of matter, which is supposed to be at the origin of the universe. So we don't see magnetic monopoles. What's the reason of that? So there is a model, there is a formalism, which is supposed, or which at least this is what we know today, is the most popular model, which tries to explain all these problems of the lambda CDM model. And this is what we call inflation. So the idea is that at the beginning of the universe, in a very, very, very small time, So there was an exponential expansion of the universe in such a way that all the particles which today come from different directions, they were before inflation, they were actually in one point, and they inflate, and after inflation they now expand in a different rate, but at the beginning they were connected, and this explains this this is, so to say, a solution to the horizon problem, and it can be shown that it's also a solution to the fine-tuning problem, and it's also a solution to the monopole problem. So the idea is then we take Einstein gravity, which is the lambda CDM model I was talking about, and we add a different field, an additional field, which is a scalar field we call phi of t. So, and then we have practically two parts of the universe. One is the standard perfect fluid I was talking about. So, and then we add a new component, which is the scalar field. For the scalar field, this is practically given in terms of this energy momentum tensor, in which the density of the scalar field is given in terms of these derivatives of phi, which is supposed to depend on time, plus this potential. And for the pressure, we take also this component, which is practically the kinetic energy of the scalar field, plus minus this potential. So the idea is now we take the perfect fluid plus inflaton, and then that part in the evolution of the universe here before reheating, that part is called inflation, and then everything is okay in the sense that starting from a time which is approximately 10 to the minus 36 seconds after the beginning of the universe, after the Big Bang, then we can explain inflation. So this part of the scale factor is very well known now with this model, with this inflaton model, and then it expands in the same way we were talking about as a perfect fluid. So that means if we now combine these two models, one is the scalar field, the second one is the perfect fluid model. So these two models are now added in order to have an explanation of the evolution of the universe, which goes back until the beginning of inflation, which, as I told you, is a very small time, 10 to minus 36 seconds approximately. So this is how we now understand our universe. This is the most popular model for the explanation of the universe. There are many problems with this model. One of them is that, as you can see here in the expression for the pressure, we have this m. This m represents the mass of this scalar field, which is called the mass of the inflaton. So this scalar field is supposed to be represented by the inflaton, and according to the theory, if there was an inflaton at the beginning of inflation, and we need it in order to have inflation, then there should be some consequence of the existence of those inflatons, but unfortunately we don't see them today. So then the standard cosmological model is Einstein gravity, which we believe is the best theory which explains gravity, an equation of state, an inflaton of mass m. So, but the problem is that we don't detect this inflaton. So the question is there an alternative way to explain inflation, to explain the evolution of the universe without the inflaton? Because we don't see it. So, in fact, there are many possibilities, but I'm going to explain what I believe is the simplest model for the evolution of the universe, including also inflation, including also some ideas about what we call the pre-inflationary era. So this is exactly GTD. So the idea is that instead of using the equation of state, sorry about that, instead of using this equation of state, the barotopic equation of state, we will put the GTD, the whole formalism of thermodynamics and geometrothermodynamics in order to explain the universe. So to do that, we have to assume something which is very important. This seems to be sometimes not true, but sometimes one can show that this is true. So let's just assume that our universe, the entire universe, is a thermodynamic system. So standard classical thermodynamic system, which has some volume V and an energy U. That's it. That's all I need in order to introduce GTD as an alternative way for explaining the evolution of the universe. So this is the main idea. The main idea of standard cosmological model, the problems that it has, and how we are going to present a different way in order to explain the same evolution the way we see it today. So now I'm going to change a little bit the subject because I need to talk about GTD, which is something more mathematical. So if somebody has a question at this moment, I would like to answer it because then I will have to change the subject. Is there any question there? No questions?
Not yet. Well, not well.
Okay, great. It means everything is clear. I'm very happy that everything is clear. Great.
Yeah, to me it's pretty clear that actually you state that what was a problem of the lambda CDM plus inflation, and now you're going to say about the alternative way to explain this problem without inflation those kind of things, right?
Exactly. This is the main idea. Okay. Great. Thank you. Okay. So let's go into GTD. So let me give you an example, which is a very simple example, probably the simplest example we know in thermodynamics. Let's look at the ideal gas. So these are the equations of state of the ideal gas. We know that it's a very simple thing. It's a very simple system. And we know that from these equations of state, we can get all the information, all the physical information about the ideal gas. Okay. This is very well known. What is not very well known is that the same information you have here in the equation state, you can have also in the fundamental equation, in which you have the entropy, which is given in terms of the n, the number of particles, Kb, which is the Boltzmann constant, a logarithm of U. U is the energy of the gas, and we also have this V, which is the volume of the gas. So with this fundamental equation, we also assume that it satisfies the first law of thermodynamics, which is du equal to Tds minus Pdv. In this way, we introduce now the new variables, T, which is the temperature, and P, which is the pressure. So this is something very simple. You can see that if you take this fundamental equation here, the entropy in terms of U and V, and you apply the first law of thermodynamics, you will find immediately the equations of a state. That means the information which is given in the equation of state is exactly the same that you have in the fundamental equation. This is, from now on, when I'm going to talk about a thermodynamic system, I will always mean the fundamental equation of that system. Okay? Not the equations of state, because it's a little bit more complicated to work with them, but we know that we can obtain all the information of the equation of state by using the fundamental equation. So from now on, thermodynamic system is equal to fundamental equation. So Legendre transformations. We know that classical thermodynamics is invariant with respect to Legendre transformation. That means if we start from U, which is the thermodynamic potential, and we make this transformation U equal to F, which is a new potential, in terms of U, is given U minus Ts. This is called a partial Legendre transformation, in which you go from U to F, which is called the Helmholtz energy. You can apply this partial differential transformation in order to obtain this new potential. You can also go from U, the internal energy, to make this transformation, and you obtain this new differential, the new thermodynamic potential, H, which is called the enthalpy. You can also apply this transformation, and you obtain the Gibbs potential. So the main point now is that you can use, in order to describe the ideal gas, you can use U, the internal energy. You can use F, the Helmholtz energy. You can use the enthalpy, or you can use the Gibbs potential. Classical thermodynamics is invariant with respect to Legendre transformations. the physics of the ideal gas does not depend on what kind of thermodynamic potential you are using. Okay, you can use U, F, H of G, whatever you want. This is the same physics. And this is very important in order to construct a formalism which is based on differential geometry. So this is two things we know about the ideal gas. And in principle, this is the same for any system which can be described in terms of two thermodynamic variables, in this case, U and V, as we started from here. So that means the entropy, the fundamental equation, depends only on two variables, U and V. This is what we call the number of degrees of freedom of the system. So we have 2 degrees of freedom in this case for the ideal gas. So now let's put some geometry. So the ideal gas is this fundamental equation. So S entropy in terms of U and V. Let's construct an abstract space in which the points of this space are U1, for instance, this is the coordinates of this U1 and V1, U2 and V2. And the idea is this: these two values, U1, V1, U2, V2, they satisfy this condition. They satisfy the equation, the fundamental equation for the ideal gas. That means that any one of the points we have in this space can be considered as an equilibrium state of the ideal gas. So all this space with all these points, which we'll call it equilibrium space, and we'll name it, denote it with this calligraphic E. So this is an abstract space. The points in this space are equilibrium states. So the question now is, can we understand, can we explain the properties, the physical properties of the system by using only the geometry of this equilibrium space? This is the idea. So instead of doing geometry and doing thermodynamics, we do geometry and we think about the possibility of explaining physics by means of geometry. So this space, of course, will have different properties depending on what kind of system we are analyzing. For instance, we have the ideal gas, we have a system, because we have a particular fundamental equation. If we change the fundamental equation, we will change the properties of this system. So the main point now is it possible to describe the physics of the system by using the geometry of this, the geometric properties of this space? And the answer is yes. And the way to do it is by using GTD. There are other formalisms in the literature, but they are not invariant. So the idea of GTD, that it is invariant with respect to Legendre transformation. So I will explain some details about this formalism, but the main idea, and what we know today after something like 15 years of work on this formalism, is the following thing. So we have a sort of dictionary in which on this part of the dictionary we have geometry, on this part of the geometry of the dictionary we have thermodynamics. So if we have a thermodynamic system, we can associate to this thermodynamic system an equilibrium space, the same way I just explained. So the equilibrium space, the possible states of equilibrium of this thermodynamic system. So from the point of view of geometry, we can show that this space is a Riemannian manifold. That means it has a metric. I will show how to calculate this metric. We have a metric, we also have a curvature. So the curvature of the equilibrium space is interpreted as thermodynamic interaction. So this is, we now can show that for all the system we have analyzed so far. If we have singularities at the level of geometry, these singularities are represented, or they represent phase transitions at the level of classical thermodynamics. At the level of geometry, we can also analyze geodesics. We know that what geodesics are. We introduce some very particular properties for this kind of geodesics. We call TD geodesics or thermodynamic geodesics. One can show that the thermodynamic geodesics, from the point of view of geometry, are equivalent, or they represent free quasi-static processes. One can show that in thermodynamics, the thermodynamics invariant with respect to the change of representation. Remember, I had for the ideal gas the entropy given in terms of U and V, internal energy and volume. I can rewrite that equation in terms of, so that U comes as the thermodynamic potential, U in terms of S and V, so in terms of the entropy and the volume. So the idea is I can change between entropy and energy, and the properties of the system are the same. So this is represented in GTD from the point of view of geometry as an invariance of this equilibrium space with respect to diffeomorphism. That means there are coordinate transformations which represent a change of representation at the level of thermodynamics. And finally, Legendre transformations, as I was explaining, we know that classical thermodynamics is invariant with respect to Legendre transformation. That means with respect to the change of potential, the semantic potential. So this is equivalent to the Legendre invariance we introduce into this formalism in order to have an invariant way to describe the physics of the system. So this is what we know today. How do we know today? So this is a schematic representation of GTD. So in GTD, we have, depending on the number of thermodynamic degrees of freedom of the system, suppose we have any number, a positive number, a positive integer number, and this is the number of thermodynamic variables we need in order to explain the system. So in order to do GTD, we need to introduce something which we call the phase space, which is denoted here as GT calligraphic. So this is this big space, this gray space, this gray space I have here, which is a curved space from the point of view of differential geometry. So this is a 2n plus 1 dimensional space, manifold. So in this space, there are many subspaces. Those subspaces are n-dimensional subspaces. All of them, in principle, as shown here, should represent thermodynamic systems. For instance, in the case of n equal to 2, the phase space has 5 dimensions, and this E, which is a line, which, so to say, this is some graphic representation of no curvature. This represents the ideal gas. So the ideal gas has no curvature, has no interaction, and everything is fine. There are much more subspaces of this big space, this phase space, in such a way that different thermodynamic systems are represented geometrically as in this way, which I showed that graphically. Okay, this is the idea of GTD, but all this has been done using the standard methods of differential geometry. So this is the main thing of GTD. So there is a big space, the phase space, and inside this big space, there are in principle, an infinite number of subspaces, n-dimensional subspaces. Each of them, subspaces, they represent a thermodynamic system. So some of the ideas again. Then GTD is a Legendre invariant geometrization of classical equilibrium thermodynamics. The Legendre invariance means, from the point of view of thermodynamics, that we can use any one of the different thermodynamic potentials in order to describe the system. The physics of the system is always the same. So, Legendre transformations are important because they have to be considered in this formalism, and this is exactly what I already explained. These are the Legendre transformation in the case of a system which depends on only two variables, in this case S and V, entropy and volume. So the whole formalism has to be invariant with respect to these transformations. So some notations in order to put some formula. So phi, capital Phi, represents any thermodynamic potential. That means it could be U, it could be the internal energy, it could be the entropy, it could be the Helmholtz energy, it could be the Gibbs potential, any one of all the potential we can obtain by applying Legendre transformation. So phi represents any one of them. Extensive variables are represented by E with an index A. A goes to 1 to N, which N represent the numbers of degrees of freedom of the system. So in the case of the ideal gas, the extensive variables are the entropy and the volume S and V. The intensive variables are the temperature at P and P. They are obtained by using the first law of thermodynamics, so that we can take all these variables as coordinates of a space, and that space is the phase space we were talking about. So the phase space then has the coordinates ZA, and the idea now, some geometry, is that the phase space can be equipped with a metric, which is GAB, capital A, capital B. These are the coordinates AB. And so one of the metrics, I'm going to show only one of them. We have several of them, but the idea is almost the same. The metric for this phase space can be represented in general in this way. Very simple way. We have here phi, one of the coordinates of this space. We have I, we have E also. So it's a combination of Y. Y, all the coordinates are here. So we have, now I have a question from Saikat. Could you please explain once
Can you see the question?
Yes. Can you please explain everything and what does the bigger space and the subspace represent? Okay, let me go back. Here, the bigger space is what I call the phase space. What do we need it? We need it in order, they are space of what? Space of what? Okay. So this big space is necessary in order to introduce the invariance with respect to Legendre transformations, which, as I was explaining, is very important for classical thermodynamics. If you want to have a formalism which is invariant with respect to this transformation, one of the ways to do it, and probably the easiest one, is to represent this transformation, Legendre transformation, as coordinate transformations. In order to do that, we have to introduce this phase space, which is a bigger space. Okay? In the case of the ideal gas, it's a 5-dimensional. So it represents, each point of this space represents all the variables you should use in order to explain any system with two thermodynamic degrees of freedom. Okay? So in the case, for instance, of the ideal gas, each point here, which is the ideal gas, each point represents the extensive variables, and the points around the ideal gas represent the temperature, the pressure, and whatever thermodynamic potential you want to use to describe it. So each point in the big space represents the possibility of having there a particular thermodynamic system. This is the big space. The smaller space, which is the equilibrium space, represents a particular thermodynamic systems. So we need the big space in order to introduce Legendre invariance. This is necessary. And the small space is necessary in order to have there the thermodynamic system living. So that means, which this is what I was trying to explain here. So for the big space, the phase space, we introduce a metric which is invariant with respect to Legendre transformation. So each point there, each point in this big space represents the possibility of having on this point a thermodynamic system. Once I choose one particular point for a thermodynamic system, excuse me, then I'm introducing a subspace, which is this equilibrium space. The equilibrium space is defined mathematically as a smooth map from the small space, equilibrium space, to the big space, the phase space, such that this is called the pullback. The pullback of this particular one form is equal to 0, and in the same way introduce a metric, which is GABG, the small indices. This is the metric of the equilibrium space, which is given in terms of the big metric, the metric of the big space, in this way. That means if I have the big metric, so I can calculate the small metric. That means I have the big metric for the big space, which is Legendre invariant. The only way to have Legendre invariance is by introducing this big metric, this big space. And inside this big space, we have several, in principle, an infinite number of subspaces, or each of them represents a particular thermodynamic system. Did I answer to your question? Are you okay with my answer? I hope so.
Okay. Um, 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 well, I think so. Yeah. I think.
Okay,
Yeah.
great. Maybe I will present some examples. Maybe it is okay. Thank you. Okay, great. I will give some examples. For instance, this particular metric G, for in the case of n equal to 2, that means we have a system with two thermodynamic degrees of freedom. So how do I calculate the metric? So this is the metric. Let's look at this metric. Well, we have here U, which is the internal energy. We have the derivative of S with respect to U. We have derivatives of S of the entropy with respect to V, and so on. If you give me S, the entropy, in terms of U and V, I can calculate this metric. So if we do that, for instance, for the fundamental equation of the ideal gas, you will find that this metric, exactly this metric, this term is equal to 0. This term goes 1 over U squared, and so on. So this metric, one can show that the curvature of this metric is equal to 0. That means flat. The space, the Krümer space of the ideal gas is flat. No curvature, no interaction. It's exactly that dictionary I was showing at the beginning. One can change S, the entropy, the fundamental equation. You will obtain a different metric. For instance, if you put van der Waals, you will obtain a metric which is not flat. So in that case, the curvature of the Krümer space represents the interaction, the van der Waals interaction. So we know that for all kinds of different thermodynamic systems, like laboratory systems, like black holes, like cosmology, as I'm going to show you. Okay, so we know that for sure. This is the way one calculates the metric. So now, this is an important step because, as I told you, there are many subspaces which represent a thermodynamic system in this big space. Now, let's take only those spaces which are extremal in the big one. Okay, that means, so there are many here, many subspaces. Let's take only those which are included as extremal subspaces in a space. So this is some sort of geometric condition, which is called harmonic map. This is very well known in string theory. In string theory, what you have in 2 dimensions, you have a string. It is embedded in a bigger space, which is, in the case of bosonic string, is 26 dimensions. So the main idea is here. So I would like to take only those spaces which are extremal in this big space. So the equilibrium space should be extremal in the big space. So this is what we call in string theory the non-Bogoto action is given in this way. That means the volume of the small space is given in place. The action of this volume is given this way, and if you calculate the variation of this action, the non-Bogoto action, then put it equal to 0, you obtain the motion equations for that, which are given this way, which you can see is a generalization of the harmonic equation, with, in this case, with some particular components, Christoffel symbols, which represent the non-zero curvature of this space. So the point is now that you have differential equations for the components, for the variables which describe the system. So what happens if we take these differential equation and we find solutions? Solutions means that this particular thermodynamic system has extreme volume in this big space. So This is something which is very well known in variational calculus. So we found some solutions of that, and I will go to show only one of them. Let's take a two-dimensional case, so a five-dimensional big space. In that case, the variables we have to consider, okay, to put all here in these differential equations. And the variables we have to consider: entropy, energy, volume, temperature, and pressure. We put all that here, and we solve this set of 5 differential equations. So we can see that one particular solution is this one. This is a solution with S, the entropy depends on U, the internal energy, and V, the volume. Here also have the volume. So we have some constants C1, C2, alpha, and beta are constant. So this is a particular solution. There are many, many solutions we have found, but this is the one I'm going to show you, because this is the one I'm going to use in cosmology. So this particular differential fundamental equation is supposed to satisfy the first law of thermodynamics, and from there we can obtain the temperature, as you can see here, and also P, which is the entropy. That means this fundamental equation should contain all the information about the system we are going to describe by using this fundamental equation. Okay? Now, let's go back to cosmology. So, again, we have the Friedman, Lemaitre, Robertson, Walker metric, which is given here. We have the Friedman equations. Before that, we introduced an equation of state in order to close the system to solve this set of differential equations. Now, let's do a different approach. So, instead of using the equation of state, for instance, the barotropic equation of state, let's use GTD, the entire formalism. Which, remember, if you give me one fundamental equation, I can extract all the information about the system. I can extract all the information about the corresponding equilibrium space. So let's use GTD. So GTD means you have a system, a thermodynamic system, and if you have a system, remember, you have a fundamental equation. Let's take as fundamental equation exactly that equation that we found as an extreme solution of this variational problem. So this is the fundamental equation of the universe. And I will show that from here, you can obtain the standard cosmological model and also the inflation, the inflation without using a scalar field, because what we have here is just a thermodynamic system. So this was the idea of introducing at the beginning that postulate. Let the universe be a thermodynamic system. And it is a thermodynamic system. It has to have a fundamental equation, which is given here. So S is the entropy of the whole universe. U is the energy of the whole universe. V is the volume of the whole universe. C1, C2, alpha, beta are certain constants we have to choose. Okay. Then how we calculate the volume to put this into the geometric model we have from the Einstein theory. So the volume we consider as A cube, which is the scale factor cube. This is approximately what we understand as the volume of a particular model with this metric. So the density is U over V, it's very simple. So, and the pressure can be calculated by calculating also the derivatives of this fundamental equation with respect to the volume, with respect to V. So from here, we can obtain all the information. Let's take a particular value of this fundamental equation. Let's put alpha and beta equal to 0. So alpha is equal to 0, beta is equal to 0. One can show that if we choose now C2 over C1 as 1 over 3, you obtain a radiation-dominated universe. So you go back to integrate Friedman equation, and you obtain exactly what we had in the lambda CDM model. If you choose C2 equal to 0, you obtain a matter-dominated universe. And if you choose C2 over C1 equal to -1, you obtain a vacuum-dominated universe. That means we can reproduce exactly all that we have in the standard cosmological model, in the lambda CDM model, just by taking different values of alpha, beta, C1, and C2. So this is exactly what we do in the standard cosmological model. In this sense, we reproduce, in this case, what we know from the lambda CDM model. So it's exactly the same information, nothing new here. So let's look at the general case. Let's take alpha different from 0 and beta different from 0. So one calculate the pressure, one calculate the density, and so on, and we can go back to the difference to the Friedman equations. You can solve them. And so I have here the expression for the pressure, the expression for the density, and so on. The point is that you can always integrate the system in such a way that, for instance, if you choose C2 over C1 as minus 8 over 9, then you will obtain a number which is very important for inflation. It's the e-folded numbers, which represent the numbers, the number of times that the universe evolves during the inflation exponentially. So this is the definition of n, the e-folded number, and for different values of C2 over C1, we obtain either 70 e-foldings, 60, 50, and so on. These are exactly the numbers we need in order to explain the inflation, in order to solve the problems I was mentioning at the beginning. So the horizon problem, the fine-tuning problem, and also the monopole problem. So that means that, in fact, by using this particular combination of these constants, C2 and C1, you can reproduce inflation at least at the level of the time it has to increase in order to solve the problems of the lambda CDM model. So, and also, there is something interesting, because remember, we can have here all the information of the thermodynamic system. If we go back on time, this is the representation of the pressure, and this line here represents the beginning of inflation. I am just drawing here how the pressure of the universe evolves in time during the inflation. Inflation is here, where x is equal to 1. 1.2 is, so to say, it's a part of the inflation, 2 is part of the inflation. So from 1 to the right, we have inflation. Before that, we have pre-inflation. So the important point here is that we were looking for phase transitions. Remember, again, we can obtain all the information of the fundamental equations. And from the fundamental equation, we can see that, in fact, during inflation, there are no phase transitions. It's a very simple thermodynamic system. Before inflation, we have these peaks we have here. They represent phase transitions. That means that starting for inflation, we have the universe as a thermodynamic system, which is very simple. There are no phase transitions at all. It's a very simple thermodynamic system. The problems start before inflation, which means this part, when x is smaller than 1, we have phase transitions. So the interpretation we have here is the following. So we had a universe which we don't understand. It was in non-equilibrium phase, because when you have phase transitions, it means you cannot use standard equilibrium thermodynamics in order to describe the system. So the universe was in a non-equilibrium phase. We have to use a different formalism in order to explain the universe before inflation. Once this phase transition happens, then the universe entered into a phase, the inflationary phase, in which there are no phase transitions. Then it goes into the radiation era, into the matter era, with no phase transitions. So it's a very simple thermodynamic system, and this is how we understand now the universe. So remember, we had two parameters, actually 40 parameters. C1 and C2 became fixed in order to have the number of e-foldings we need in order to solve the standard problems of the lambda CDM model. So this idea of having here a phase transition before inflation and having here these numbers, you obtain these numbers by choosing a particular value for alpha and beta. So alpha then is this value 10 to the minus 78. Beta is 10 to the minus 84 meters. The interpretation we have of that is that beta represents the volume of the universe at the beginning of inflation. And as far as we know, it is the only model which can say something exactly about the beginning, about the volume of the size of the universe at the beginning of the inflation. So this is the beginning of inflation, and this is very well because this is far away from the Planck volume in which we expect other kinds of effects. So alpha is some parameters which relates somehow the interaction between the particles during the time of inflation. We don't know exactly what that means, but well, this is something we have to explain. So we have two-phase transition before inflation, and this is what we call the universe was in a very strange phase. There was a phase transition, and this phase transition was in order to come from a state in which the universe was outside the equilibrium to a state in which was in equilibrium, and from starting from the inflation, everything is very fine because there are no phase transitions. The universe is, so to say, very simple from the thermodynamic point of view. So this is what we call background cosmology, in the sense that we can reproduce the beginning of the inflation, okay, the time when the inflation started, 10 to the minus 36 seconds. We can reproduce the end of the inflation, 10 to the minus 32 seconds. We can reproduce the number of unfoldings. This is what's called background cosmology. However, there were several effects during the inflation. This very tiny, very tiny period of time, there were many effects which were very important in order to have what we see today in the universe. So one of them is reheating, which means that the universe, when it expanded very quickly, the temperature went down. One can reproduce that also with our model, and then it had to reheat in order to have the particles we see today. One other problem is because the graceful exit, which means that inflation starts at some point, but it should end also at the end of the inflationary era. So in order to solve that, we have to change the model, and also, so what we did in order to explain the reheating and the graceful exit was the following. We have a model in which during inflation, we put the combination of three different fluids, so to say. One is the inflationary fluid, in the sense that we have exactly the same fundamental equation we used in order to explain the background cosmology, the background inflationary cosmology. So exactly this one with the same value. So then we have some entropy for the radiation and some entropy for the matter. So then we take exactly the same fundamental equation with those particular values we had, which is alpha and beta. Alpha and beta is equal to 0 for radiation, is this part of the fundamental equation, and alpha and beta, C2 is equal to 0 for dust. So that means we have this. This is inflation, the first part of the fundamental equation. The second part is radiation, and the third part is dust. So if we now take this combination, instead of only one fluid, we have three fluids, so to say, of three thermodynamic systems. So we can solve all the problems of reheating, graceful exit, and also if we use this combination of entropy, this combination of fundamental equations in the Friedman equation, you can solve the system, and then you will see that if you evolve those system of equations, you will see that at the end you will have an effective dark energy, which is some sort of cosmological model. However, we don't have a cosmological model. Remember, the way we do it today in order to explain the dark energy is we introduce a term with a cosmological model at the level of the action. We have to change the theory. That means, no? Here we don't change the theory. We are just changing the universe from the point of view of thermodynamics. So we are taking three different fluids, and so we can solve all the problems that we usually have in the cosmological, in the standard cosmological model. So, some sort of review of we have done here. So, we have the fundamental equation of the universe we obtained from GTD. This is the fundamental equation here. Entropy given in terms of the energy, given in terms of volume. The energy is rho times the volume, which is volume, as what I mentioned, is A cubed. Then we have a model for inflation, in which the inflation starts at 10 to the minus 36 seconds. It ends at the time 10 to the minus 32 seconds. We have a value for alpha, which is one of the constants of GTD. We have a value for beta, which is another constant of GTD, which we interpret as the volume of the universe at the beginning of the inflation. And we have also some very particular choice in order to reproduce inflation, which is C2 over C1 equal to minus 8 over 9. So, from the point of view of GTD, during inflation, because alpha and beta are different from zero, then you have the equilibrium space. Remember, this abstract space, the small space, is curved. That means we have some curvature there, and this curvature represents the interaction, the thermodynamic interaction between the fluids. These are the fluids during the time of inflation. There is some thermodynamic interaction during this time. So this is the interpretation we have. Then, after inflation, which is at time 10 to the minus 32 seconds, so we have lambda CDM model, which, as I told you, we can represent exactly the same with alpha equal to 0, beta equal to 0, and C2 over C1 taking different values. So that means starting from this differential, this fundamental equation, we can represent the evolution of the universe first as a curved equilibrium space, and then when alpha is equal to 0 and beta equal to 0, one can show that the equilibrium space is flat. That means no thermodynamic interaction. So the history of the universe is very simple. At the beginning of inflation, because of that phase transition that we have before the inflation, we had a system in which there is a thermodynamic interaction. The particles during the time of the inflation, they were interacting. Once inflation ended, there is no more interaction between the particles from the point of view of the equilibrium space. The equilibrium space is flat. So it's a very simple system from the point of view of thermodynamics. First, we have some interaction, very simple interaction, and then we have no interaction at all. Today, we have no interaction at all from the point of view of thermodynamics. So, in that sense, we can reproduce the standard cosmological model without an inflaton, without the problem of the scalar field. So we have that fundamental equation, which represents only particles which are consistent with the standard model of elementary particles. So, but remember at the beginning, I was saying that the universe is homogeneous and isotropic. However, if we go down from this large scale, we see that the universe is not isotropic and not homogeneous. We have galaxies, we have clusters, and so it is not homogeneous at all. So in order to explain that, there is something which is called cosmological perturbations. We did exactly now from the point of view of GTD, which means we have the density, and we introduce a perturbation, delta rho of the density. We have the pressure, we introduce a delta P of the pressure, and so on. We have also a metric perturbation, and then we have to solve the new field equations in which we perturb the Einstein's equation, we perturb the Einstein tensor, and we also consider a perturbation of the energy momentum tensor. So this is something that is very well known in cosmology. This is perturbation in cosmology, and then you have to solve the system. So the point is, I'm not going to go into the details of all this calculation. The point is that there is something that is very important when you make these transformations, these perturbations, which is called the power spectrum. The power spectrum is the kind of solutions you obtain when you solve these differential equations, the perturbed Einstein differential equation. So for this kind of solution, there is a particular number which is very important. This is n. which is called the power spectrum index, which is a quantity that you can measure. This is the spectral index has to be of this order of magnitude, 0.96, in order to explain the existence of galaxy clusters, of galaxies. So if you have a different number for this index, then you have the structure we see today at intermediate, at mid scale. So scales that are not so large at the large scale. So the point is, can we reproduce now with our method, with our perturbation, can we reproduce this number? So we solve the differential equations, a very large thing to do in any case. So we can see that what is called the power spectrum, we obtain exactly the same solution, and we can reproduce this number by using this value, this epsilon 0.066, which is a combination of C1 and C2, by taking beta, which is the volume of the universe, with the value we obtained at the beginning in order to explain inflation. That means that our model, once we consider also perturbation, our model can also explain the structure of the universe at the level of cluster of galaxies, at the level of galaxies, because the perturbation gives exactly this number, the spectrum index, which is necessary in order to explain what we see. So, conclusions. We propose a different way, an alternative way to do cosmology, which means we don't use a particular equation of state. We know that it works very well, but it also has many problems. So we suppose that the fundamental equation of the universe has exactly this form, in which the entropy depends on the volume, on the energy, the entire energy of the universe, and the volume of the universe, with some constants which we fix by using what we observe today. With this model, in which, remember, we have no scalar fields at all here. This is the main thing. We have only a particular fundamental equation, because we suppose that the universe is, in fact, a thermodynamic system. This is the main point here. Now, starting from here, we can reproduce the evolution of the universe, starting from the time in which it was 10 to the minus 36 seconds, also very early epoch in the evolution of the universe, until today. So we can reproduce anything without any flatten, without a scalar field. So, but also we can go back from to inflation. This is the question I'm asking here. What happens when the time is less than 10 to the minus 36 seconds? So, from our point of view, but now we are working on this because we don't know exactly how to do that. There was, before inflation, there was a time in which the universe was outside the equilibrium, non-equilibrium states, which we cannot describe at this moment, because in order to do that, we have to change completely the method we are using. We have to somehow construct the formalism of non-equilibrium GTD, which we don't know now. So we believe that starting from time 10 to the minus 44 seconds to inflation, in which we had phase transitions, so our universe was in a state of non-equilibrium. Then, before this Planck time, of course, which means from t equal to 0, the Big Bang, to the Planck time, 10 to the minus 44 seconds, so there was a different era in the evolution of the universe, which we call the quantum era. This is what we expect, so to say, theoretically. In order to explain that, we need a different formalism, which is not GTD, what we call quantum GTD. So we are right now working on developing this formalism, which is not simple at all, but, well, we expect to have some results in the following year. So we are working on non-equilibrium GTD, on quantum GTD, in order to explain what happened with the universe before inflation. Okay? And before inflation, we have the quantum era and the non-equilibrium era. So these are the main conclusions and some references of the papers we have been publishing in the last 7 years with some colleagues, with some students. Was Christine Gruber, who was a postdoc at our university here. I have been working with Orlando Luongo, who was a former student, now is professor at the University of Camerino. And right now we are working very, very intensively with Jesus Anaya, who is a student, PhD student right now here. He's working here at the UNAM in Mexico and also in Camerino with Orlando Luongo in Italy. So these are the main references I wanted to show you. The main results are given here in these papers, but there is nothing at this moment I can say about non-equilibrium GTD and quantum GTD. So I expect to have some ideas about that in the next years. As I was telling you. So this is the main idea of the GTD applied in cosmology, and this is the results we have today. Thank you very much.
All right. Okay. Thank you very much for this very, very interesting talk. I think I myself am not working in the cosmology, but I'm interested in the technique. Actually, you apply from thermodynamics perspective to explain explain cosmology, right? Which is actually very interesting. I have a question at the very end about quantum GDT. You mean that actually, if we have that kind of quantum version of GDT, it's kind of like you're going to quantize your face-to-face somehow, or you is that right?
Well, I hope so. Let's say I hope so. I don't know exactly. So
All right. Okay.
the idea is the following. Okay, remember this is a problem related to quantum gravity. So this is why you expect the quantum era being there. But nobody knows how to quantize gravity. So, however, we believe that from the point of view of thermodynamics, it is simpler to talk about some quantum properties of a thermodynamic system. So what we want to do is to quantize, so to say, the equilibrium space. And if we quantize the equilibrium space, of course, the phase space is going to be quantized too. What's the meaning of that? So right now we are working with a PhD student on some so to say quantum metrics, which are supposed to generalize this metric I showed you at the beginning. So to say the classical metric. You have the classical metric, quantize them in some very particular way, and these quantized metrics we are going to apply in order to try to understand this quantum era. No, this is the idea, but it is quite complicated because, well, these metrics, it is very difficult to find the quantum information we want to find. It's quite difficult because these quantum metrics are put by hand, so to say. They depend on the fantasy of the author. There are more than 10 different quantum metrics. We're using all of them, but we don't know how to obtain from there the information we need in order to explain the universe. So, but we are going exactly in this direction. So, finally, we believe that it's a pure mathematical problem, and we are working on that too.
All right, I think so. Yeah. Somehow this is kind of reminds me about information geometry, which actually we have kind of feature law matrix, right? This is like a classical version that actually you have 2 point on the plot manifold, right?
Yes.
And you have also a quantum version of this feature law matrix. Is this? I'm not sure. This is the way you explain things. Is this somehow kind of analogy of what I had in mind with this kind of feature law matrix?
Exactly. This is information geometry in the sense of the Fisher-Rao metric. And let me explain a little bit about that. We have our GTD metrics, okay? Our GTD metrics are some generalization of the Fisher-Rao metrics because the Fisher-Rao metric is not invariant with respect to Legendre transformations. Our metrics are invariant. So this is why I believe that our metrics are in some sense better from the geometric point of view than the official raw metrics. So
I see.
from the point of view of information geometry, people know how to quantize, so to say, quantize the official raw metric. These are the metrics I was talking to you. I was explaining. We are using them, but we have also our own metrics. Now we want to quantize our GTD metrics. So it is not easy. It is not that easy. We don't know exactly how to do that,
Yeah.
but this is one of the steps where we are going to try to go in order to
see.
explain this quantum era.
I see. Because your face is somehow very special because
Exactly.
it's equipped with some kind of very interesting feature. Actually, you need all the point actually invariance under the Legendre transformation, right?
Yeah.
That is a very special feature of your space.
Exactly.
Actually.
Exactly. Mhm.
Yeah. I think there is. I'm not sure there is a question from the online or not. Yeah, I think there is a question. Yeah, can you see the question? Oh, I
Yes.
have from
That's a good question.
Oh, yeah. Okay.
Okay. Can you also see the question, or should I read the question so that everybody knows?
Oh, you don't need to read the question. You just maybe just start to answer
Okay.
right away.
So the first question: can you explain more about beta as the initial volume of the? Oh, okay. Well, beta is a number which we obtain from comparing the values we know for the inflation, which means the start of inflation and the end of inflation. So we have two numbers, which is the time of the beginning and the end of the inflation. And we have also n, which is the number of withholdings. So we obtain this number. The main point here now is that that number, 10 to the minus 84 cubic meter, is very small, but it is not that small as the Planck volume. It is bigger than the Planck volume. The volume is in the order of 10 to the, if I correctly remember, 10 to the 105 cubic meter, something like that. Okay, so that means we are very safe with our number because we expect that first the universe at the Planck era was of that magnitude 10 to the minus to 10 to the 105 cubic meter, and then it expands. So it goes on to 10 to the minus 84. Sorry, I'm talking all the way around. 10 to the minus 105 cubic meter. Then it expands until 10 to the minus 84. So that means that that particular value was the value of the universe when the non-equilibrium phase came to an end. So this value is very important because it so to say, we start from this value, it fixes all the other values. It fixes the end of the inflation. It fixes also the starting point of the reheating. I didn't mention that here, but it is related to all these parameters, all these problems we have during the inflationary era. So all of them are related. So this is what, okay, we have this number. It's safe in the sense that it is what we expect physically. So we hope to understand the non-equilibrium era in the evolution of the universe and the quantum era of the universe and the evolution of the earth, and then we will have some more ideas about what's the meaning of this particular volume, which is just the beginning of the inflation. So this was the first question. The second, I don't see now the question.
Cham, can you bring again Alberto question on the screen? Yeah. Yeah.
Okay, the phase transition is driven by R of no. Remember, we have two geometries, so to say. The geometry of general relativity, so, and we have the geometry of GTD. They are different things. So, phase transitions, they happen at the level of GTD because the R of it is the curvature of the equilibrium space, not the curvature of the Friedman-Robertson space. No, that's space-time. So we have a space-time with a curvature. We have equilibrium space with a curvature. The curvature of the equilibrium state is the one which says when phase transition is happening. So they are not related at all. At least we don't know any one of these relations. So how could we write GTD into tetrad fields? Oh, it's very simple. Tetrad field for GTD. So you have a metric. You have a metric for GTD. I gave you explicitly the form of GTD in 2 dimensions. So then you have to introduce the tetrads, well, the orthonormal tetrads, whatever you prefer, non-tetrads, whatever. And you can use the formalism, the standard formalism of the Cartan formalism of differential forms. And you will obtain, well, the same thing you obtain in tetrad formalism. So it is very easy to apply this. I would say it would be nice to have these, the GTD formalism in tetrads. But at this moment, I couldn't say what would be the advantage of using it. But in principle, it's possible. It's not a problem to do that. Okay. It might lose the transition for torsion. Oh, okay, yes. Torsion. Indeed, we are applying Riemannian geometry. That means we use from the very beginning the condition that torsion is equal to 0. Of course, you can introduce torsion. It's a possibility. We know, for instance, that in the case of general relativity, the introduction of torsion is very important because it gives us a different point of view of at the geometry of GR. So one could do that here. So, for instance, I would say that it is possible to explain the curvature of GTD also with a torsion instead of curvature. So if that is if it is a way to predict an inflation, I don't think so. I think inflation is something very physical. So we can reproduce geometrically what happens during inflation. We can reproduce that. It is very easy. It's just a mathematical tool. So, but predict inflation, I would say the prediction of inflation is exactly what I talked about today. The prediction of the existence of inflation is that the universe undergoes a phase transition, actually 2 phase transitions during the non-equilibrium era. And these these phase transitions, they mark the end of the non-equilibrium era and the start of the inflation. So this is the prediction of inflation. So inflation is predicted by non-equilibrium GTD, so to say. No? But we still have to work on this method.
Okay. Okay, another question from Chilapap. Yes. It's quite a long one.
The inflationary epoch energy of inflation transfer to the matter particle. Why do we expect observation? Okay. Why do we expect to observe inflation field after inflation? Well, I don't expect it. Actually, well, this is the problem of the inflaton. Okay. This is the standard, or should say, the standard cosmological model with an inflaton. So if you put, and this is exactly what people did, you put a scalar field with a mass, and you need the mass. You cannot put m equal to 0 as the mass of the inflaton, because if you put m equal to 0, you don't have the end of the inflation. You have something which is called eternal inflation. So m is very important. The mass and the inflaton is very important in order to end inflation, to have a final time for the inflation. So that means that there were some particles which we call inflaton. They existed during the time of inflation. During the inflation, many particles were transformed into other particles. Which is what we call then the nucleus instance of heating and so on. So all the analysis of this inflaton field is that they could transform. Of course, m, the inflaton, could transform into other particles. But when they transform into other particles, those other particles, they should have some information about m. And this is the idea. This is how people do astroparticle physics. M should be somewhere in the particles we see today. There are different models to explain how it should be there. And people have been doing experiments for a long time. No inflaton has been observed so far. So So this is the main problem. Astroparticle says as the inflaton should be here today, Not even M, not necessarily M, but some, so to say, some remnants of M, but they are not. So this was one of the question. Now, can I see the second question?
Yeah, Chan, can you bring it again? Ajahn Thirapat question. Yeah.
Okay. The gravitational could be described by formalism of thermodynamics. Could it? The gravitational interaction could be described by formalism of thermodynamics. Yes. But this is somehow a different topic, because remember, gravity is very well related to thermodynamics. This is something we know for like 30 years. Okay, in the following sense, you can write Einstein's equation as the first law of thermodynamics. This is how people. This is what people say. But Einstein's equation are just pure thermodynamics. Okay, it could be, but nobody knows that for sure. It could be that gravity is just some sort of effective force or something different, which is usually called entropic forces. So, entropic forces are very known in quantum chemistry, which are the way how many chemical systems evolve, and based on the fact that any evolution has to go in the direction of the increase of entropy. So this is what they call the entropic force. So it could be. There are some models to explain gravity as entropic force. So you can do that with our formalism. Actually, it's very easy. No? One can show that different theories correspond to different equilibrium spaces. For instance, the equilibrium space of the Einstein theory is flat. It's very simple. In the case of, for instance, other theories, I don't remember now. I work a lot sometimes with Horava quantum theory, so to say. And for that theory, one calculate the equilibrium space, and that the equilibrium space turns to be non-flat. So that's to say, yes, we can work in this direction with GTD, but our results are not conclusive. We cannot say that gravity is entropic force, which means gravity is not fundamental. Okay, so but the formalism can be applied in principle, to any theory, in which you can find a fundamental equation. Okay, so we can work in this direction. There was one more question which I don't see now.
Yeah, Chan, can you bring it again? Question.
Okay.
So yeah,
GTD formalism is the whole system, the universe, assumed to be a thermodynamic. Yes. If yes, how the universe was in dynamic equilibrium after Big Bang, but before inflation? Okay. Okay. The question. Okay. How the universe was in thermodynamic equilibrium after Big Bang? It was not. Okay. After Big Bang, I don't know what happened. The universe was in a quantum state.
Yeah.
We cannot describe that. We hope to do that with quantum GTD. We are working on that. So it was not at all in equilibrium. So after the end, once this quantum state ended, we believe, because of our results, that the universe went into a state of non-equilibrium. So we cannot describe the universe also in this non-equilibrium phase, because we don't have a non-equilibrium GTD. So the main point here with GTD is that the prediction of GTD, once inflation started, everything is in equilibrium. Everything. So that means the universe was outside the equilibrium, first in a quantum state and then in a non-equilibrium state for a very short period of time. 10 to the minus 36 seconds. So, which is a very complicated phase. It's a very, very tiny phase, but it's very complicated. So it was not in equilibrium before the inflation. So one of the predictions of our model is that from the point of view of thermodynamics, our universe is very simple. Inflation, a little bit interaction during inflation, then interaction disappeared, and now we are here in a very simple. Actually, one can show that our universe today is very similar to an ideal gas, with no phase transitions, with no interaction, a very simple system. Okay, but before inflation, things are very, very complicated. No equilibrium at all. I think this was the
Okay.
last question.
I think so. Yeah, I think so. Yeah. Um, I think there is no more question from the online, and so I think it's well, we are here together almost like 2 hours.
Oh,
I
sorry.
think. Yeah, but I do enjoy a lot because I learn new things a lot from you.
Okay.
It's very interesting. Um, actually for the people actually watching online, if you have more question about this kind of stuff, I think you can send the email to the professor Hernando later, right? Or you can look at the reference that actually he gave at the very end about his list of paper.
Yeah.
Look at that. And I think this is about time. I would like to thank Professor Hernando again for spend time with us, 2 hours for this very very interesting talk. Thank you very much. And yeah, that would be the end for this colloquium talk. Bye, everyone. See you again later. Thank you very much.
Okay. Thank you very much to everyone for being here. Thank you very much for the questions. So, and again, thank you very much for the invitation.
Right.
Thank you.
Okay.
Goodbye.
Bye bye.
Goodbye. Good night. Good night. Good morning there.
Yeah. Yeah. Okay.
Okay.
Yes.
Bye bye.
Bye bye.
Bye bye.